Now the relation less than or equal to is the prototypical partial order. And so an arbitrary partial order is often denoted using a variation of this symbol with curves like so. So new definition, a relation R on a set S is irreflexive if no elements in S or no element in S is related to itself. That is, for every element X in the set S, X is not related to itself. So new definition, a relation R on a set S is a strict partial order or we may say a strict partial ordering on the set S if it is irreflexive and transitive. The relation less than is the prototypical strict partial order. And so an arbitrary strict partial order is often denoted with a curly variation of the symbol for less than, like so. New definition, let the set X together with this relation be a poset. An element X in the set X is a minimal element if there does not exist an element Y in the set X such that Y is distinct from X and Y precedes the element X. An element x in the set X is the least element of the set X, and this is denoted min X, if for every element Y in the set X, X precedes Y. So note that a least element, or I should say the least element, if it exists, is by definition a minimal element. In fact, it is the only, if it exists, it is the only minimal element. However, a minimal element even if the only one need not be the least element. So new definition. Again, let X together with this relation be a poset. An element X in the set X is a maximal element if there does not exist an element Y in the set X such that Y is distinct from X and Y succeeds the element X. And an element X in the set X is the greatest element if for every element Y in the set X, Y is succeeded by X. So note that a greatest element or the greatest element if it exists is by definition a maximal element. And in fact, if it exists, it is the only maximal element. However, a maximal element even if the only one need not be the greatest element. And the greatest element of the set X is denoted max X. So very soon we will begin considering extrema or extreme values. And by extreme values, we mean the maximum or minimum element in a set. So let's move on to functions. A function from a set A into a set B is a non-empty relation which will denote F. That satisfies the following conditions. One, for every element A in the set A, there exists an element B in the set B such that the ordered pair AB is in the function. And if the ordered pair AB is in the function and the ordered pair AC is in the function, then B and C are the same element. So the first condition is known as an existence condition. Every element of A must be paired with an element in the set B. And the second condition is a uniqueness condition. Every element in the set A is paired to only one element in the set B. Now the set A is called the domain of the function, and this is sometimes denoted DOM of F. The set B is called the codomain of the function, and the range of the function, which is denoted RNG of F, is the set of all the elements in the set B, in the codomain B, where there exists an element A in the domain such that the ordered pair AB is in the function. That is, the range of F are the elements in the codomain that are mapped onto by at least one element in the domain. So I use the word map. So let's talk about some notation and other terms for a function. So if f is a function from the set A into the set B, this is denoted this way: f colon A right arrow B. And if the ordered pair AB is in the function, this is denoted f of A is equal to B. So another term for a function is a map or mapping. And that terminology gives us a way to, suggests a way to visualize a function. So consider a set A being mapped into a set B. So we have elements in the set A, elements in the set B, which is the codomain. To have a function, every element in the domain must be mapped onto at least one element in the codomain. But it is permissible for two separate elements in the domain to be mapped onto a common element in the codomain, and we still have a function. Now, we need to be able to recognize a function by looking at the ordered pairs. So this function diagram or map diagram gives us the function containing the ordered pairs A1, B1, A2, B2, and A3, B2. So again, for a function, it is permissible that elements in the codomain appears twice with distinct elements in the domain. However, each element in the domain can only be paired to one element in the codomain. So again, with notation, this ordered pair A1, B1 is denoted f of A1 is B1. And we have f of A2 is the same as f of A3. Both those elements A1, A2 and A3 are mapped onto the same element, B2. So new definition: a function which will note f from A into B is a surjection or surjective function if for every element in the codomain B there exists at least one element A in the domain such that the ordered pair A, B is in the function. That is, the function from A into B is surjective if and only if the range of the function is the entire codomain B. That is, every element in the codomain is mapped onto by at least one element in the domain. So let's look at a map diagram for a surjection. For simplicity, we'll just have three elements in the codomain. For a surjection, each element of the codomain must be mapped onto by at least one element in the domain. It is permissible that an element in the codomain is mapped onto by more than one element in the domain, but each element in the domain must be mapped onto by at least one element in the domain A.